meet hydrogen. Symbol H has 1 proton and the atomic mass is 1.008. So the atomic mass represents the mass of the protons and the neutrons. So when we talk about the atomic notation, this is about how we represent atoms and elements. So in this case, you can see I've written this number here as your atomic number. And the number at the top is your atomic mass. So I can think of this as the protons plus the neutrons. That's how we get that. It's the mass of those things. Therefore, if I went from this form where I've got atomic number, atomic mass, symbol, and I wanted just a generic situation. So how could I represent any single atom regardless of what it is? So we use this form. We'll call X, which is just the atom or the element, whatever it is, the thing. Z is our atomic number still. So the atomic number is always on the bottom, and the top is our mass number, or atomic mass, sometimes we call it. It doesn't really matter. Same thing. Atomic or mass number. So this is our general notation. We use this. A is atomic mass, Z is atomic number. So now if I'm talking about some sort of a reaction, if I had this thing and it either decayed or reacted or mixed with something, and say I've still got that thing, but it also now gives me something else. So let's say it gave me hydrogen. This thing produced hydrogen. Hydrogen has an atomic number of 1 and an atomic mass of this. So conservation applies here. We had conservation of energy, conservation of mass, all of that stuff. This still applies in atomic physics. So if I started with Z, number of protons, and I've now got something plus 1 proton here, this thing must have what I started with minus 1 to be balanced. So here I've got Z minus 1 plus 1 gives me Z protons. So that's all sweet. On this side, I now must have A minus 1.008 protons. That's my atomic mass. So whatever this is, it has Z minus 1 protons and A minus 1.008 as its atomic mass. So this is an example of how we would use atomic notation. It has to be balanced. I can't just create or subtract mass, and I can't add or subtract protons from nothing. They have to come from somewhere. Let's take an example. Here I've got cobalt, so its atomic number here is 27. So like we talked about before, this is what we would call the Z, the atomic number. So this is the Z value. The mass number at the top is our A, so mass number. So if we were given this, we don't even need to know what it is necessarily, but straight away we can say, whatever this is, it has 27 protons, and it has 59 as its mass number. So if I add its protons and its neutrons, there's virtually 59 of them. So I can work that out. If there's 59 protons plus neutrons and 27 protons, that means this actually has 32 neutrons. So I can calculate how many neutrons the thing has. Earlier in a previous video, I mentioned isotopes. So we can't change number of protons because it would no longer be cobalt. If I added one, it would be a different element. But I can add and subtract neutrons. And that's where I get isotopes. So if I had cobalt 2759 and I added 1 neutron to it, this affects this. It would now become what we would see as cobalt. Didn't change this. This is still 27. But I've added 1, so it's now 60. So the key here is still cobalt, but it now has 60 instead of 59 neutrons. And this I would write as cobalt 60. So So this is the notation we use for writing an isotope. I'll write what it normally is, and I've signified that something is different. In this case, it's 60, meaning it has a 60 atomic mass. 60 protons plus neutrons. If I was to work the other way around, and I gave you this, and said, how many protons, how many neutrons does cobalt-60 have? You need to work backwards. So firstly you say, okay, cobalt-60 means it's cobalt, this is 60, I don't know what this is yet. I can go to a periodic table and look at cobalt and find it and be like, okay, there it is. And cobalt is number 27. So my periodic table will tell me that. You don't need to memorize that. I look at the original atomic mass and it was 59. This has to be 27 because atomic numbers never change. But it's gained 1. So if I do the same math before, in this case, we had 32 neutrons. Now we're going to have 33 neutrons. And in both cases, 27 protons. So that's cobalt-60. There's a whole bunch of examples. One of the big ones that we'll see as we go along is something like U-235. That's a very significant one. That's weapon-grade uranium. So U-235, that is the same concept. That means it's going to be uranium with 235 here, and the atomic number, I'll just write Z for now, is whatever uranium is. But we've changed something here. We've either added neutrons or we've taken neutrons. So that's our isotope notation.